All right, so any questions from yesterday's lecture? I assume silence means assent. Okay, so today what we'll be doing is the following. So yesterday we did phase space and the concept of trajectory on phase space. Then we saw how we can think in terms of geometry of things like pendulum. Right? So any dynamical system, how to think of it in terms of pictures. And then we looked at fixed points and their stability. And how do we linearize and thereby look at slope of the function f of x. So if dx dt equal to f of x, then the stability of the fixed points can be found by looking at the slope of function about the fixed point x star. All right. But this is of course all having to do with one dimensional systems, that is where x is a scalar. Okay. So today we will be looking into two dimensional system, and from there you will try to figure out how to do it in general for higher dimensional system. So and then I said I will do numerical solution, which I couldn't get to. So today we will start from that. So we will look in particular at a method called Euler method. So advanced methods like, there are other methods like the Ranjakota implicit methods, which I will not touch upon, because basically to make a start all you really need to do is learn Euler method, and the rest you can pick up once you know the basic concept. And for most practical purposes, you will always have some integrator already built in any of the languages you use. There will be libraries with this numerical solvers. So depending upon what's your purpose, you might want to choose a stiff solver or an implicit method or something like that. Oh yeah, then so this is what we are going to do. So this was what has already been done. So if you have any questions about this, you should ask me now. Then we will work with bifurcations. So this, as I said, is the very close analog of phase transition. In fact, we do see things like critical exponents here also. Okay. And in particular, we will be working with the three bifurcations, namely transcritical. There are only three types of bifurcations that can occur in one dimensional systems: saddle node and pitchfork, and we will see particular examples of these. Okay. And then we will see an example of an imperfect bifurcation. So this is a very simple example of what is known as a catastrophe. So catastrophe is a name which was given by the mathematician René Thom. So in the 70s, catastrophe theory was the complex adaptive systems of today. So if you wanted to study something like society or riots or so on, you do catastrophe theory. So we will see why. Okay. So we will look at the simplest of, or one of the simplest catastrophes, the so called cusp catastrophe, and we will use the example of taken from again population dynamics. So just as we saw this fixed points and the stability in the context of, so the example we used was population growth. Okay. So just to be consistent with that example, I will again use population dynamics, but just as you can do apply these concepts to any other dynamical system you can think of, similarly you can apply this for other systems, and I will do a fun example of how dogs behave. Okay. So, take it with a pinch of salt, because it is actually meant to be more as an analogy rather than an exact description, and once I do it with a dog, you will realize you can do it with anything. Yeah, and then hopefully I will have time to then go on to 2D systems. Okay, so which is when things really become interesting. All right, so this is the scheme of things to come. Okay. Oh, so there was one thing I wanted to talk about, but didn't get chance to talk about, which is like, what does this have to do with things like potential energy. So, we know that systems, physical systems tend to go towards lowering their energy, right. So, one can of course write down a dynamical system for which one can define a potential energy, okay. And so then how do we connect dynamical systems theory with physics? Okay. So, it turns out that you can, for example, use Newton's law. So, again I can use something like the definition of so this is basically a definition of force, okay, but I can also think of this force as coming from the potential energy. How? So, suppose you have a potential energy which looks like this, okay. So, this is V, this is x, okay. So, suppose you are here, which way will you go? Sorry? Towards positive x, or rather you go downhill, that is the main thing, right. So, if I look at it in terms of the slope, what will it be? Negative of the slope. So, basically I can think of this as minus the spatial derivative of the potential energy function, okay. Now, so looked at in terms of a dynamical system, I can say that my dv dt, where okay sorry, so this V stands for velocity, while capital V stands for potential. So, dv dt equals, I can use the chain rule, right. So, if I use the chain rule, what will I get? dv dx and then dx, oh I am so sorry, sorry, here I meant again my notation itself got confusing for me, sorry, I meant suppose you now look at how does the potential energy change with time. So, I can write this using chain rule as dv dx dx dt, okay. Now, what is this? This is just this quantity that I already looked at, right. And what is dx dt? Dx dt is just simply the velocity, okay. So, now since my m dv dt, so dx dt is simply v, and so d2 x dt2 can be written as m dv dt. So, that was simply minus dv dx, okay. So, for the moment I will simply take my mass to be unity, okay, just to reduce complications. So, now I can replace the dx dt as uh,
Isn't force always like a partial derivative of the potential?
yes.
Here we have the.
Yeah, so I'm just, you know,
I think it's on.
if you want, you can just do it like this. I'm just like saying that for the moment, I'm just considering potential as a function of x only. Yeah, but you're right, it will also change with time. So now I can say that, but what is this? This is simply now from dx dt, I knew that the force is dv dx. So from this, I can essentially write it as so dx dt has let me see mv potential is fx dv dx. Okay, so let me see. I should get a dv dx whole square. How did I manage to mix that up? So this is my force. So m into f gives me dx dt. So dv dt gives me minus dv dx. So okay, so I think I made some mix up over here, because eventually what I should get is minus of a square, so which is always less than 0. So let me see where I made the mix up. dv dx dx dt dx dt it's one of those cases where, you know, like Murphy's law, just when you think that you would do something quickly, things tend to get completely mixed up. So
The first you can write dvt as a dv of v.
yeah, so yeah, so for a first order system, I can write my yeah, so dx dt for a first order system, I can write as minus dv dx, okay, because this is a simple first order system. So there is because it's just a first order system. So you assume that there is enormous amount of damping and so on, so that you can reduce it to first order system. And so this now becomes dv dx whole square. And so this is a quantity which is always less than 0, because this will always be a positive quantity. So now this means that with time v will always decrease with time until you reach the point where v equal to 0, okay, or rather the fixed point. So at the fixed point v cannot change anymore. So once you are there, dv dt is set to 0, and so this means that the fixed point corresponds to the minimum of v. Now this is a very, very special case, because, you know, I am only looking at a system which, because the problem is if I write this down, I have to look at a two-dimensional system, okay. Now in a 2D system, we have not yet approached 2D systems, okay. So if I want to reduce it to just a 1D system, I have to essentially consider an extremely what do you call frictional system. So something like, you know, a particle rolling down, let's say a bowl of molasses or something, so that you can reduce it to just a first order differential equation, okay. Because the moment you have the normal system, you will basically have to consider this fact. So basically, you know, it will basically keep rolling back and forth until it kind of settles down. Here you are not giving it this chance of rolling back and forth. Here you are saying that it's basically so viscous, the medium in which it is flowing, that it just steadily goes down and then settles here. So then I can basically write that velocity would essentially be going as this. So velocity gradually steadily decreases as you go down the slope until once the slope is 0, it just stops. Okay. So this basically shows what's the connection between energy minimization, which is what we do in statistical physics, and convergence to fixed point as in dynamical systems. So this is the StatMech approach or statistical physics approach, and this is the dynamical systems approach. Did I manage to confuse everyone? If you got confused, please ask and I will just, okay, fine. So let me try to do it slightly differently, okay. So suppose you are moving in a very highly frictional system, right. So in a highly frictional system, it's not just this, right, there will be an additional term. What's that additional term? Frictional force. How will I bring in frictional force?
Proportional to
Sorry?
something proportional to the velocity at which
Yeah,
you
so something negative, right? So basically it will become minus gamma dx dt. Correct? You okay with this? So now what I'm doing is, essentially I'm saying that, okay, what if I do this? So m dv, sorry, now I'm saying divide everything by gamma. So this is m by gamma d2x dt2 minus dx dt, and now you have this force, okay. And so what I'm saying is m by gamma, this is so small that I can neglect it compared to this term, okay. So once I can neglect it, I can write it this as dx dt equal to or minus del v del x rather.
It would be plus. It should be plus.
that first definition.
Well, okay, so let me do it this way. Which way will the force go? So the force is tending it towards the positive x-axis. So there will be del v del x, okay. And so now I'm putting this minus. So it is just minus del v del x, right?
It should be plus gamma.
Sorry?
It should be plus gamma dx.
Uh,
The force is going absolutely.
Oh yeah, you got it right.
Oh, you're saying that I should put this here, yeah. But then it just gives a minus me
No,
over here.
plus minus.
So you're saying, no, so you're saying force and then what?
Minus gamma dx. You take a body and make a free body.
Mhm. Okay, so you're saying that this is the frictional force, and so therefore I do this, yeah. Right. But anyway, so this will give me this dx dt equal to minus force minus del v del x, and so therefore I get this quantity, which is what I wanted to show. Okay, yeah.
No, you're supposed to get dx dt equals positive force.
Dx dt equal to
Force, not net. But it
So in that case, I think that term
yes.
becomes the force.
Sorry.
yeah, force is minus dt.
Yeah. So okay. So let me write simply like this. So dx dt simply becomes minus del v del x. Okay. Sorry about those sign problems. So finally, what this gives me is this quantity. Is that fine? Okay. So now I see that okay, there's not that much difference between the StatMech approach of energy minimization and a convergence to a fixed point by looking at these flow fields. Okay. So often you would see that what we do in dynamical systems is so in the phase portrait that I drew yesterday, I had some f of x, right, and so we found that if it goes like this, then I know that what the arrows are, and then from these flows I can see where it will go. Okay. So now what I find is that this picture is actually equivalent to this picture. So if this is dx dt versus x, then essentially I can think of this as essentially a flow like this. So dx dt versus x. So this and this pictures are kind of equivalent, although this is shown as a, you know, in the space of v and x, and this is shown as dx dt versus x. Okay. Okay. Now numerical methods. Okay. I hope it's everybody, the sign confusion got sorted out. Okay.
Say this is like a particle moving through a viscous fluid in a tube. Like this is
It's a particle which is moving in a highly viscous medium, let's say on a bowl. Okay, so you put the bowl, let's say it's a, or rather it's a section of a bowl that you cut so that it's effectively a one-dimensional system, and you put the whole thing in jelly, okay, and then you let a marble flow through. So what will it do? It's very gradually settling down to the bottom of that cup. Okay, that's how you can think of it physically. Okay, so how to numerically solve a dynamical system? So yesterday we saw how you can, from a discrete system, turn it into a continuous differential equation. So now this time we will do the opposite. So suppose you look at a function like this, dx dt equal to f of x. So I can use my old calculus knowledge to write it as, so how do I write dx dt? I say this is xt plus delta t minus xt divided by delta t, okay, equal to f of x. This is just standard calculus. And then I do a nudge nudge wink wink and I say, okay, provided delta t is very small, I can rewrite it as can you see it? Why? Okay. Okay. Now, so this is the trick. So provided this is true, provided delta t is very, very small. Okay. All right. So this is the so-called Euler method, where what you do is you start with some knowledge of initial condition, x naught, and you find out what is x at time delta t by just evaluating x f of x at the initial condition. So, f can be any function, you just plug in the value of x naught and multiply delta t with it, and you add it to the initial value of x naught. Okay. Now, the $1,000,000 question is, what is delta t, right. So, delta t must be small enough such that this is valid. Okay. Now, the practical problem would be if you make delta t ultra small, like 10 to the power minus 16, it will take forever to integrate over anything, right. So, what you do is you try out various delta t's and you have this following argument. So, you say that I will try with delta t equal to something like a, okay. I get what is x at delta t with as a function of a, and then I say that, okay, suppose I half delta t and I say that for a by 2 what is the value of x, and then I ask what is the difference between these two. So, what I have done is I am halving the time step. If the error that is incurred is much less than half, okay. So, let us say the error is just less than 10% or even lower, then I know that, okay, with this delta t I am incurring an error which is much less than the factor by which I am decreasing my time step. Okay. So, usually one uses such a rule of thumb to ensure that the delta t you are using is reasonable to use. Okay. The problem with Euler is this. So, what is happening? So, suppose your trajectory is going like this. Okay. So, provided, so your delta t is like you are taking steps, okay. You are walking and you are taking steps like this. So, basically at every time step you are evaluating the slope in some sense. So, what is dx dt is nothing but the slope, right. So, you are estimating the rate at which your speed is changing, and using that you are just taking a step. Okay. So, as long as your steps are much smaller than the rate at which this function is changing, you are safe. The problem will come when you have a something like this. So, now what you suppose you are taking steps like this, right. So, you come here and you take a step which takes you from here to here, you completely miss this spike. Okay. So, you have to ensure that your delta t has to be smaller than any large sudden or any quick changes that happens in the system.
But if I take a large enough delta t like that,
yeah,
can I make that approximation?
Yeah. So, the thing is that you have to have some knowledge of your function, how much it can vary and so on, to be able to use that accurately. That is true. If you have a completely unknown function, then often it is possible that you can get it terribly wrong, and this is the problem of working with canned programs where you do not have any access to the solver, which is, so you can have a software which is doing all the solutions for you, right. And like for example, there used to be this general neural simulator Genesis program where you would give some how many neurons you want to simulate, which is connected to which and so on, and you just find out the time series, right. So, I was teaching Genesis to a group of students, and then one student got very excited because he found something like this, that he was giving some stimulus and then immediately withdrawing it, and he found that his neuron was behaving like this, right. He got very excited. But if you are trained in numerical methods, you know that anything which works like this means that your numerical integrator has blown up. Basically, it has gotten unstable. So, that is why you are getting this very jagged ups and downs. Okay. So, you have to have a bit of experience in working out like when your system is actually getting very unstable and so on, but usually this is a fairly good what do you call rule of thumb to use, that you are mostly blowing up. I mean, this is actually a fairly what do you call wicked system to work with, which is mostly flat, except on some occasions it becomes very spiky. But for other functions, these would be varying rapidly all over the place. So there it does not matter where you look, you will very soon realize that if your delta t is not small enough, you will start seeing that there are large errors which will generate as a result of this. Okay. So this is also why we actually for serious work often do not deal with Euler, but work with things like Runge-Kutta or implicit methods or stiff solvers and so on. But Euler is always a good first thing to use. Why? Because when you deal with very large complex systems with let us say thousands of variables, okay, working with more complicated solvers becomes a headache. Okay. So then Euler is a very good method to quickly do a dirty calculation, see what you are getting, and then invest on a much more complicated numerical integrator. Okay. Because writing numerical integrators is tough. Okay. So the more complex it is, the longer it will take for you to program it and so on. This is like the very easy to simulate. So you just write it down, see whether you are seeing anything interesting, and then okay, if you find anything interesting, then you start working on a complicated enough program. Alright, any questions about this?
Calculating the slope only at the initial phase.
No. So then now the question is,
Also,
what will it be at x2 delta t? So it will be x delta t plus delta t into fx delta t, and then you find out what is at 3 delta t. It is x2 delta t plus delta t into fx 2 delta t and so on. So what you are doing is you are basically dividing up your time axis into intervals of delta t, and every point you are evaluating. So you come here and then you come here and then you come here and so on.
if the function is nice enough, I think it can guarantee some convergence.
Sorry?
If the function fx is some nice function,
Yeah.
so this will converge to the solution xt.
Yeah, so as you make delta t smaller and smaller and smaller, you will approximate the actual, let us say you analytically solve it, you will be able to exactly approach the analytical curve, right. What you are doing essentially is you are not evaluating it at all points, but only at certain points, and then extrapolating. Any questions? Okay. If not, we will go over to the next one, which is looking at bifurcations. Okay, so what are bifurcations? So let me give you an example of a bifurcation. So suppose you have a metal scale, okay. So you take this metal scale or a metal plate and you are pressing down on it. So as you keep increasing the pressure, it still remains vertical until at some point it will buckle, right. So when the pressure is large enough, it can buckle either this way or buckle this way, right. I do not have a metallic thing here, or at least nothing that will buckle in my hand, but you get the idea, right. I think I do not quite see anything that will easily buckle unless I break it. That isn't that too light? That's like okay. Shakti has very kindly lent me his name badge, but you can see, right? If I press very lightly on it, nothing happens. But then if I press, it could go either this way. Sorry, it could go either this way or this way. Okay, so there are two possibilities. So just imagine doing it with a metal scale. Okay. So what is happening here is that until I give it a sufficiently high pressure, nothing happens, sufficiently high force, and then beyond a critical pressure it suddenly buckles either this way or that way. Okay, and the buckling would increase as I increase the force on it. Okay, so if I think of it, it's like this. So this is, let's say, force. Okay, and this is basically measuring the deviation from this vertical, okay, the maximum deviation from the vertical. So it will remain 0. So here the deviation from the vertical is 0 until at a critical force there are two possibilities. Either it will buckle and go like this, or it will buckle this way and go like this, and this solution is still possible, but it is unstable. Okay. So it can happen that I have gone beyond the force that will cause it to buckle, but it is still just about holding on, and then a little change in my hand's orientation will suddenly cause it to buckle by a huge amount. Right? So this is an example of bifurcation where the nature of the solution now completely changes beyond a critical value of the parameter which I am tuning. Okay. So the point at which this takes place is known as a bifurcation. So like, what is bifurcation? When a road comes and breaks into two, we say that it has bifurcated, right? So in this particular case it has gone in two ways, but occasionally it need not be just two ways, it could also be something else. So for example, take the case of the logistic equation. Okay. So remember what it was, dn dt equal to Rn into 1 minus n by k, right. Now consider R. Okay. So what will happen when R is negative? If you are not sure about it, just think of it this way. So this is your dn dt, this is your n, okay, and this slope is basically R, right. At very, very small values of n, it is just a linear curve R into n, because you can ignore, so small n you can ignore this, basically this just becomes 1, right, because n by k is much, much smaller than 1. So you can just take it to be Rn, right. So this is just Rn, right. Okay. When R is negative, what will happen? Yeah. So when R is negative, it is actually like this, right. So this is R positive, this is R negative.
It will not grow.
So what will happen to it?
It will just stay towards n equal to 0.
It will go to 0,
Yeah.
right. So now this is actually the unstable point and this is the stable point, right. So if this is my R, all through this negative, okay, I should use another color. It is 0, okay. What will happen beyond R? When R is positive. So exactly at R equal to 0, what will happen? So it's just this line. Right? So that means it's neutrally stable. Anywhere you start from, it will just stay there. You move it, it will stay there. Right? So this entire line is trivially going to be an equilibrium. Alright? At r equal to 0, it doesn't matter. Okay, so this is x, sorry, n. So it doesn't matter where you are. Wherever you start from, you will be there. Now, for any r which is 0 plus, what will now happen? So now it has changed where this becomes unstable and this becomes stable, right? So this will become like this, right? Now the important thing to note is that this solution still exists, but it has now become unstable. And conversely, this solution was always there, but shoot. So what they are doing is that they are exchanging the stability, the two solutions. Okay. So this type of exchanging of stability is also a type of bifurcation. So this is also a bifurcation. So this is an example of what is known as a transcritical bifurcation, whereas this was an example of a pitchfork bifurcation. Why pitchfork? Because it looks a bit like this, right? Okay, and we have another example called saddle node. Okay. So what's a saddle node? So let's look at that.
So the negative growth rate case,
That's realistically not feasible. That does not exist in reality.
No, it's
You can
a
have
situation like in sink habitats where the resources are much smaller than that can sustain any population. So that sink habitats will have growth rate which is negative. So that means even if you bring a population there, they will just eventually die out.
Yeah, but if you bring population beyond the carrying capacity, the unstable fixed point, it would still die out, or it would explode, right? I mean,
Sorry?
like, look at the inverted curve,
Yeah.
and you have the unstable fixed point here. So if you introduce a population suddenly,
Yeah.
which is larger than that,
Okay, yeah.
blow up.
Yeah, so that's the obvious problem with this, but that's because essentially you can, the idea is like you are going to start from, so it only is a valid description as long as you're somewhere here. Okay, all right. So the thing is that what is happening is if you bring in, let's say 100 people, the next generation will be only about 50 people, then 20 people and so on, right?
But can we have this seen like chemical populations? Like,
No, so first of all, yeah, so this is a kind of what you call, I mean, this is simply not valid for systems which you make very large. Okay, so it's a bug in the system, you might say. So you could argue that there, close to it, it's just behaving as Rn. Okay. So the carrying capacity, okay, it's a good point. Actually, what you are saying is that the carrying capacity itself has no meaning in a sink habitat, right? Because it cannot actually sustain anything beyond 0, right? So ideally I should just write it as a dn dt equal to Rn. So this was just basically to show you what is a transcritical bifurcation. There are better examples of transcritical bifurcation, but I just wanted to stick with population growth, which is why I showed this, okay. But to be truthful, carrying capacity has no meaning there, because the system cannot sustain any finite population, right? Good point. Okay, so again sticking with my population example, let me now show you an equation which looks like this. Can anyone guess what this is describing?
These as in
So first of all, what does the dn dt look like?
cubic polynomial.
Hmm?
Cubic polynomial.
A cubic polynomial. So what are the roots?
0, alpha, and k.
Okay.
It's a bistable system.
So what will it?
It's a bistable system.
It's a bistable system. So that means how does the curve look?
This part.
So here will it be positive or negative?
Negative.
Negative. So essentially this means that this will flow here, well, negative does not mean anything, and it will flow here. So this is positive, this is unstable, sorry, this is stable, unstable, stable. Okay. Now what is the actual meaning of, ecological meaning of this? Why would populations behave like this? Yes. So this represents something which is known as alley effect. Okay. So it basically says that if the population goes below a sustainable number, it's doomed to extinction. Okay. So if you have population below a certain sustainable level, then they are as good as dead. I mean, they are extinct, they just don't know it yet. Okay. So, so there is a critical population below which you will go to extinction almost certainly, and above which you will go to the carrying capacity. Now, imagine that you add a certain number. So what is this? Plus a. What would this mean? Sorry? Or some kind of an influx. So if it is plus, that means influx. If it is minus, that means it's efflux going out. Okay. Now, suppose I plot n star, which is the equilibrium, as a function of a. So a positive. So here you got influx, and here you got efflux. Okay. So what will you see?
N star are the fixed points.
N star are the fixed points. So here for a equal to 0, it's this. Okay. So how will it behave if I make a more and more positive? Sorry? Okay, so but before that you tell me what will happen to this curve. So if I add a to it, that means I am taking the entire curve and lifting it, right? So what is happening to my fixed points? So this one is coming closer to this one, and this one is moving further away, right? So if I keep doing this, eventually what will happen is this stable fixed point and this unstable fixed point are going to meet over here, and they are going to annihilate, because if I increase any A any further, they just disappear. Okay, you only have one stable fixed point now. So how do I see this over here? So I can draw it like this. So this is my unstable branch, this is my stable branch, and this is another stable branch. So here what is happening is my unstable and stable are eventually coming together and then disappearing. This is an example of a saddle node bifurcation, or sometimes known as blue sky bifurcation. Why blue sky? Because if you look at it from the opposite end, so as I gradually increase my A, suddenly out from nowhere another stable and unstable branch appears out of the blue sky. Okay. What if I make A negative? So if I go make A go negative, this is going to start going down until this unstable branch and this stable branch collide, and if you make A go down even further, then they have disappeared. Now for the particular example I am giving, which is population growth, a negative end does not mean anything, but there could be other systems where actually this thing is not at 0 but at some finite value, right. So there it may make sense, right. So I will just, even though I know n does not make sense, I will still nevertheless draw it this side. So basically this is going lower, lower, lower until this is annihilating here, whereas this one goes like this. Okay. Now in the particular case of population, since I cannot go to negative numbers, it just means that this is 0 population, the population is extinct. But for a particular value of negative A, let us call it AC1 or ACL to stand for lower critical value, I can have a stable finite population, okay, which is an equilibrium, right. So on the other hand, there is another critical value, A critical, upper critical, where beyond a certain value there is only this upper branch, there is no lower branch possible. Now what will happen if I increase or decrease A? So suppose I am increasing A from this side, sorry, what am I saying, decreasing A. So I am on this branch because here there is nothing else possible. So I am going like this, and then suddenly at some critical value of a flux, without any warning I just go to extinction from a large finite population. So it seems like disaster, right. I mean everything was going fine, okay, my population was just decreasing slowly, 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 and then suddenly nothing.
But
right.
Those fixed points would also appear. No?
Which fixed points? Yeah, but I can't go there now because I am on this. So there is this unstable thing which is a boundary, okay. In any perturbation it is going to get me go back here, okay. Now at this point suddenly the, let's say this is a settlement, population has gone down, okay, so like do something. So they will say, okay sir, we will just make it slightly less, so we will we won't allow people to go further out. But the problem is if you go here you are still stuck here, right. So you keep increasing the A, and you find that instead of going back here it is just increasing very slowly, okay, until at this point suddenly there is a huge rise in the stable population. So this gives you two examples of two things which you are very familiar with. One is that this is an example of a discontinuous phase transition or a first order phase transition. So going from a finite value to 0, and hysteresis. Which way you change A matters, which way you are coming. Are you coming from a large population to low population or from a low population to large population can alter your course or what you see. So for the same value of A here, you could be either here or here depending on where you coming from, a high population side or a low population side. Okay. So this is an example of hysteresis. And if you remember your if you have had training in statistical physics, you will remember that hysteresis is typically associated with discontinuous phase transitions. Okay. So voila, you see that in dynamical systems. Okay. 3:30. Okay, so I am supposed to end now. Just to very quickly tell you that I was using various different examples. Now you might say, hold on a second. I can see maybe, okay, so this is called a saddle node. So this is a, okay, I already wrote that, saddle node bifurcation. So you might say, okay, is there a particular universal form that I can associate with each of these bifurcations? Well, yes. So this is the so called normal form. So typically a saddle node can be written as any equation which you can reduce to something like r plus x square, where r stands for the parameter that you are changing. Then I can show that as I am taking r from negative value, so r less than 0, r equal to 0, r greater than 0. So when r is less than 0 or when r is 0, what happens? This is dx dt equal to x square, so that is just a parabola which just meets this horizontal line at 0. Okay. If I make r greater than 0, there is no equilibrium because it does not intersect with this line. So there is no dx dt equal to 0, right? No equilibrium. If your r is negative, you now have two equilibria. This one is stable and this one is unstable, right? And so here these two are exactly annihilating each other and here it disappears. So this is known as the normal form of the saddle node bifurcation. So any equation which shows a saddle node, you should be able to show that it has this particular form. Okay. For a pitchfork, the normal form is cubic. It's Rx minus x cube. So if your r is less than 0, then there is only one fixed point here. If your r is exactly 0, then at 0 it is just tangential. It is just if you just look at the tangent, it is exactly horizontal, and beyond that you will have this unstable and these two stable. This reminds you of something that Rajesh did.
How to pick up that M star?
This is basically the mean field theory of magnetism, Curie-Weiss law. So if you are less than the critical temperature, your magnetization will look like this. Okay, so this is your magnetization. So you will see a minus m and a plus m, and the m equal to 0 is unstable. This is exactly what is happening at Tc. Above Tc, there is only m equal to 0. Okay. So, you can actually show this in fact, that the Curie-Weiss law, which is essentially tan hyperbolic weight. So, essentially it is the solution of this implicit equation m equal to tan hyperbolic beta into the coupling coefficient into the coordination number, that is how many spins are you talking to your neighbors times m. Okay. So, let me club all, since these are, oh sorry, since, so beta is my temperature, inverse temperature. So, let us club this Jz into a single constant, let us just call it J. So, let me just call it beta Jm, right. So, how will it look? So, this is my m and this here I am plotting f of m. Okay. So, since tan hyperbolic looks like this, for various values of beta, so as I gradually decrease my beta, in other words temperature is increasing. So, here temperature increases or beta decreases. So, at beta equal to 0, that is temperature going to infinity, this is just a flat line which is horizontal, but as temperature goes to 0 or beta increases, this becomes like this. Now, how do I find out my equilibria? That is just m equal to m, right. So, I ask where does m and this tan hyperbolic of m intersect. So, I just draw this line, right. So, here you can see there are 3 solutions, right. So, this is the negative finite value of magnetization, positive finite value of magnetization and 0 magnetization. Here also you have negative finite 0, but here you notice there is only 0. So, this corresponds to t greater than Tc, this corresponds to t less than Tc. So, somewhere here you will have the t equal to Tc line, which is at this point just the middle portion is just tangential to the diagonal line. Okay. So, if you plot this as a function of t, what will you get? So, this is your m, right. If you plot m as a function of t, what will you get? So, at very high values you will get some solution here and the symmetrical place solution here. So, let us call this and this is the unstable part, right. And then as I am gradually decreasing t, these are going towards 0, okay, and this is unstable. So, these are the 2 stable branches, and here you have only 0 as the stable branch. So, this is a pitchfork. Okay. And finally, the normal form for the transcritical bifurcation is here dx dt rx minus x square. So, which looks something like this. So, here you have a stable point here, unstable point here, here there is a merging, and then after this here is an unstable point and here is a stable point. Right. So, what you will see is that there is another. So, this is your R. So, here the unstable branch and the stable branch meet, and after that the stable branch becomes unstable and the unstable branch becomes stable. So, there is an exchange of stability. All right, so I will end at this point. So in the next class, we will start with the concept of imperfect bifurcation or catastrophe, and then go on to two-dimensional systems.